I'm Crosby. I'm CTO of a company called Swim.ai, and my contact info is there. I'm going to talk about the application domain, and I'm really grateful to David for his talk previous to this, because he saved me a bunch of effort in terms of describing the complexity of building applications that have to process data in real time. So I'm going to cover that domain. I'm immensely grateful to the Pulsar community for having me, but also for Pulsar, which is totally awesome. I'm going to give you an example of probably one of the largest applications which is using Pulsar today. Let's fly. So I would encourage you, if you're in the business of building applications which consume real-time events from Pulsar, to look at SwimOS. If you look at swimos.org, you'll find it all. It's an Apache 2 licensed stream processor that makes it really easy to build streaming applications which deliver what I'm going to call continuous intelligence at massive scale, delivering intelligence in real time. So I'm going to cover all that in much more detail, but please go have a poke around. So here's an example of an app. It's pretty easy to show you all the transit vehicles in San Francisco. And by the way, we have this for just about every other big city in the US. That's kind of only marginally interesting. What's much more interesting is a map of the current PM25 pollution in the city. Okay, and that requires fusing data from the traffic vehicles themselves. By the way, they don't have PM25 sensors on them. A little bit of physics, maths, weather data, and whatever else to put together a concurrently synthesized view of the traffic, of the pollution in San Francisco. Okay, and so the point I want to make here is that processing data and analyzing it is contextual. It's based on where the thing is, what it's doing, how fast it's moving, and a bunch of other stuff. It's based on multiple data sources, and it requires continuous analysis of the state of vehicles and the environment to deliver the intelligence. And so what we need to do really is change the stream of raw events, data from the edge, into a stream of intelligence, which we can then sell, perhaps. So, for example, we can have an API which allows insurers to get hold of this data all the time. Okay. Similarly, I can get NOx pollution. By the way, because the buses themselves or transit vehicles don't have sensors, you know, I have a little bit of inference to do here. I have a little bit of a physics model. And so what you're thinking is that although David's sketches and other algorithms are really powerful, good starting points, we have to have something which is a little bit more sophisticated in terms of modeling the thing and understanding how it will evolve over time. So my definition of continuous intelligence then is that these are applications that always have to have an answer. Okay, so it's not okay to say, wait until next batch. The data itself, the arrival events from the infrastructure, whatever we're looking at, drives stateful concurrent computation over a model. And the model here involves a bit of physics and a bit of geo and everything else. It's the arrival of data that drives the computation. Okay, so it's not a user hitting a GUI or something. It's highly contextual. You know, it's red in downtown San Francisco because there are a bunch of buses there. So the relationships between things, the notions of containment, proximity, and so on, have to be continuously evaluated, and they influence the analysis and prediction. Okay, we have to be able to deliver automatic responses to stuff. If there's an alert, we need to be able to do it automatically. And we need to do it for every bus in every city across the country simultaneously. Okay, big demands. Okay, so we're in the domain of a stream processor. Pulsar, I'm assuming, is our infrastructure for delivering these events from the raw data from the edge or from infrastructure in the cloud or whatever. So I'm not going to spend much time here. The key point is that the stream processor here is the function that's going to execute our application logic on raw events to give us the intelligence that we need. Now, there is a thing which David covered, which is effectively the fact that Pulsar functions can run within the brokers. I happen to dislike that for a bunch of reasons. Happy to take questions on it too. Pushing application logic into infrastructure is a very bad idea. Okay, so I'm going to assume the stream processor lives externally to the broker infrastructure. It's a much more scalable architecture, and it allows me to deal with the application resources separately from the resources required to move data up through the brokers. Now, what is SwimOS? So this is the entire talk on one slide. After this, you can turn off or do whatever you need to do. Look at the picture. Pulsar on the left, sending me events, maybe getting additional events, the insights delivered back to the broker. SwimOS is two layers. At the infrastructure level, we're going to build a distributed peer-to-peer mesh of instances, just deployed perhaps on Kubernetes or whatever, and they interconnect to build a mesh using WebSockets. At the application layer, SwimOS builds automatically a distributed, stateful, concurrent graph of actors, which we're going to call web agents, which concurrently compute over all of this data as it flows over the graph. And you know what? It's really easy to use. Okay, so that's the whole talk in one slide. Let me dive into it in a bit more detail. Now, here is an example of an application which is absolutely huge. We're serving intelligence on the back of a Pulsar broker for a major US mobile provider to allow them to manage the connection quality in their network. This application runs in multiple availability zones across the US and deals with hundreds of millions of endpoints and tens of thousands of base stations. And it continually and dynamically manages the connection quality, allowing this provider to maximize connection quality for all of their users. I point this out because the data rate is astonishing. Okay, so we're currently at 4 petabytes per day. It will grow to over 20. And I want to point out one really important thing. You cannot afford the storage for the data. So don't even begin to think about it. You have to analyze data as it flies past, okay? So an important component here is that this notion of store then analyze is kind of ho-hum, okay? We need to move on, people. REST and databases are not our friends when it comes to real time. Okay, so what are Pulsar's many pros? Gosh, it has thousands, and in every sense, it is the state of the art here. It's okay at event processing, okay? But I want to very clearly state that for me, that's just fine because, you know, the application layer notion of event processing should be done elsewhere. Serverless is a great abstraction, and gosh, there are tons of others. Okay, we can all make scale microservices and so on. But there's always this one big problem, and that is this database or this idea that we're going to store state in some spinning bed of Rust, okay? And I just don't like that. So let's examine a slightly different architecture. Let me point out some other problems that relate to use of the pub/sub paradigm generally for the application layer. Okay, so let's start here. So imagine I'm monitoring an engine room of something, and I have some number of microservices which are consuming events off the head of a queue, and it all looks great. Okay, so all my microservices are busy, fiddling around with the database, doing whatever they do. We're whistling while we work, everything looks fair. And you see my little clocks ticking along on the bottom here. The problem is this. At any point in time, I don't know how many microservice instances to dedicate to application they're processing. And so they could all be busy, and I could get to the tragic event, which is there is a fire in the engine room, just a moment too late. Okay, so what's the problem? I cannot dictate how many sources publish to this topic. I cannot dictate how many events they put in this topic queue. I can't really control how many microservices are consuming from the queue, and it should be dynamic. And so we end up with this problem, right? I could wake up and it's all a little bit too late, and we need to solve that problem. It gets a little bit worse, actually. It could be, for example, that there was actually quite good information early in the queue, but I just couldn't put it together in time. Okay, so for example, if the engine temperature and the fan temperature being high and the coolant volume being low indicated a good chance of something blowing up, that would have been useful to know, and I could have done something about it. But I don't have a way to do that sort of analysis. Okay, and a simple stateless microservice, which has to hit a database to figure all that out, yeah, whatever. We're sitting at the end of a database latency, which is, hey, it's 1,000,000 times slower than the CPU and memory. Did you hear me? It's 1,000,000 times slower than the CPU and memory. And that is just not good enough. Okay, so there are numerous challenges. It's not related purely to the database. So I want to, if I could plead with you to do one thing, it's get off this notion that this is fundamentally a database problem. There are gazillions of in-memory databases. Okay, it's not a database problem. You can push stuff quicker into storage, but the database cannot compute for you. Okay, the database can modify state, assuming that it is holding the true nature of the world, but it can't compute. So memory is good, but the database won't compute your metrics for you. And there are tons of other issues. So pushing all of the concurrency control, scaling, and so on into the database layer is okay, but there are better ways to do it. So what do? Typically, we drive computation from a client, and I'm going to make a broad claim here that streaming analytics is that notion of UIs asking questions or looking at stuff. And that is a real time. That's a sole problem, okay? This notion of polling the database or some logic is not real time, okay? It's driven by some consumption method. Now here's another problem. If I might just have a model of the world which says that if I had a 3D map of the engine temperature, fan temperature, and the coolant volume, I could have detected that there is a problem. Great. Where does my model come from? Well, if you believe the big cloud vendors, there is a wonderful machine learning lifecycle which tells you how to train models and then provision them into your apps, and yeah, it'll all work out. Okay. Unfortunately, in the real world, real world systems have tolerances which are different. And what if this particular engine had slightly different tolerances? And if I'd learned on this particular engine, I could have done something different. Okay, so this centralized notion of learning, training, and then deploying models to the edge, I think it's fun, but I don't see enough data scientists at work to prepare all the models we're going to need. So continuous intelligence demands this notion of data-driven computation. So forget the database. If you want to store stuff, that's fine, but analyze, then store. Okay, analysis in a granular context, everywhere, concurrently, stateful computation in memory, in a distributed fabric, and pervasively real-time computation at CPU and memory speeds instead of hitting databases all the time. Okay, but there's lots of data. Here's the little hamlet of Palo Alto, which daily produces more data out of its traffic lights than all of Twitter. Okay, so that's about 4 terabytes per day. It may be going up. Okay, and Las Vegas, which is, I think, where David was, you know, cool. It's a reasonable city. It's about 60 terabytes a day of data out of the traffic lights in Vegas. And last time I looked, this is probably out of date. Facebook was somewhere around 600 terabytes a day. Okay, there is tons of data, people. More data than we can shake a stick at, which is cool. We're in the right business, but we have to analyze it on the fly. We can't afford to store and analyze. Okay, so there's much more than you can store, and the store and analyze notion has to disappear for another big reason, which is that most data is ephemerally useful. There is no point in keeping most of it. Okay, you really don't care that the traffic light was green at the last Tuesday morning at 8:07 a.m. Okay, but you would really like to have that incorporated in some knowledge about how the system will behave from here on. Okay, so here is another app. This is traffic.swim.ai. And in this model, I'm effectively predicting on the fly from 4 terabytes of data flying past in Palo Alto, what the future phases of every one of these intersections in Palo Alto will be. And you can see the evolving predictions there in an overlay. As new data samples come in, and we continually revise, train the models, and predict and stream the results. So just as you're very familiar with raw events coming from the edge, I want you to start thinking about the analysis, the insights, as being streaming too. That is, the beautiful thing about the Pulsar stream processor model is that we can publish these intelligent observations, these predictions, back into the broker, and indeed they can be consumed, right? And indeed these are consumed by organizations that want to route their vehicles through city, so Uber, Google, whatever, okay? And so they can better use the infrastructure around them. So intelligence is driven by a flow of state changes on things, not data. And if I could plead with you for another thing, it's stop using the term data for everything. There's raw data, and then there is state. So let's fly on then. I would like to see adopted this notion of continuous stateful concurrent processing. Okay, so the lambdas, yay, lambdas are great things, but there is no such thing as stateless computing. It's just somebody else's problem. So if we make these functions stateful, then we have the ability to reason about streams as new data arrives. Okay. Streams never stop, so why store and analyze? I don't get it. Let's analyze and then store if we have to. Applications have to have an answer. I mentioned that, and the meaning of data is fundamentally contextual. Okay, when the light changes in one next door to me in Palo Alto, it will affect the traffic that arrives at my light. Okay, and so this context, this real world computed context that results from data is fundamental. Let me give you another cool example. We do a ton of work in the city of Dubai on traffic. Here's a great example. When a truck with bad braking behavior approaches an inspector, tell the inspector. Now, this is a relational model, but it's continually dynamically computed. The truck has bad braking behavior is clearly an analytical computation, and is approaching is clearly an analytical function, and it has to be reevaluated for every single data sample. Okay, you get the idea. So I'm going to introduce you Swim Web Agents. These are Swim is based on the actor paradigm. So if you're familiar with Akka or the actor paradigm in general, Erlang, you get in a heartbeat. It's very simple. SwimOS subscribes to event streams from real-world sources. So here we are, we're a stream processor. And then for every source, we're going to create a thing called a web agent. By the way, these are objects. They're concurrent actors. We call them web agents because the object ID is a URI. So we always know where to find them, okay? No matter where they're running in a big distributed fabric. Each of these web agents cleans, labels, and analyzes data from a single real-world data source. And it can do cool things like David mentioned, sketches and other things. But it's going to statefully evolve. It's an in-memory thing, and it modifies its own state. Now, here's the cool piece. Agents dynamically link to related agents, okay? Just like if I link to you on LinkedIn, I get to see your updates, okay? If one web agent links to another, it gets to see in memory, in real time, state changes on the part of that agent. Okay, so the link and the relationships are dynamically computed. Remember my example of is approaching or bad break-in behavior. Okay, so we concurrently build this stateful in-memory graph, which is dynamic and fluid and continually changing based on the arrival of data. Okay, so data builds the graph and continually changes it. And as data flows over the graph, we compute. Okay, so these relationships could be containment, proximity, and other logical relationships, or even computed, like correlation. Now, linked web agents share their in-memory state in real time. You just compute, and you use it like a local variable. Well, you just point to it, okay? So web agents are vertices of the graph, links are links, and they give you access to state. And each of these web agents continually computes on its own state and the state of its links as data flows over the graph. So data-driven, stateful, continuous computation. And then you can do anything. You can do way cool analytical things, including learning. So I have a couple of examples for you. So going back to my example on traffic, these web agents can do arbitrarily sophisticated things. They're computational entities, after all. So they can analyze their own state to determine, to go, say, from voltages to green, in the case of a traffic light. They can perform all sorts of analytics. David mentioned a bunch of really cool things like sketches and other things, distributions. They can perform interesting MapReduce style queries. They build graphs. You can do relational queries. And indeed, you can even do dynamic queries on them. And they can learn and predict, okay? And I'm going to cover that in a little bit more detail as well. Now, if you happen to have an investment in some analytical framework like Flink or in Spark, no problem. Remember, those things run on state. They don't run on data. And so web agents feeding a Spark model is a cool way to go forward. All right, so here's an example, going back to my example of, say, traffic. I have my broker sending me tons and tons of data, and the light says I'm green. Yay, the web agent for the light says I'm green. And by the way, the intersection, which there isn't a real world object there, it's another web agent registers the state. Okay. Now, as the state of the infrastructure changes, do we need to keep all the data? Yeah, whatever. Most traffic lights, for example, tell me that they're red 10 times a second. That's a waste of time. And I really don't want to save that data. So often we throw away the raw data and there's, we just save the state in memory. All right, so we get redundant information and we do it early. But for a large infrastructure, say Palo Alto or Las Vegas or Houston, we're going to end up with thousands of these web agents. maybe tens of thousands, or in my mobile carrier example, millions, hundreds of millions, each of which is managing its own state in response to continued updates of events from the broker. So the streaming data auto scales the application. It just builds, right? So for every new piece of information, every new event, either there is a web agent which can process that event, or we're going to make one and we'll link it into the graph. Okay? So it's an in-memory graph created at low cost, built by the data. It's like blowing up a balloon. Okay, so an application then is an active graph. Now here you just see a bunch of web agents, each of which is some intersection in a city. Actually, we have really cool things in Swim, which is this notion of relationships which are dynamic and computed. And we have built in a whole bunch of find functions and geospatial functions and so on. So it's trivial for an intersection, for example, to know who its neighbors are, okay? Because we know the lat and long of every single intersection. And so then the following thing is a no-brainer. Every intersection predicts continuously using its own state and the state of its neighbors, okay? And it streams its predictions back to the broker. Okay, now I want to bring this, I want to wait just a sec for you to get this model in your head. It's entirely different than the nonsense you'd hear from the big cloud providers about how you train a model in the cloud and then push it to the edge. Okay, these are effectively smart digital twins which learn on their own data and their data in their surroundings, become better all the time, and then publish their predictions continuously back to the broker. And this works in Palo Alto, and the same code without changing a line works in Las Vegas and Houston and New York. Okay, no data scientist needed. Cool. So these web agents link to make this graph. At the first tier, what I have is just the basic sensors into some virtual object, which is an intersection. Intersections link, and then the ability to continuously learn and predict, which is just a function of in Swim, but also you can interface these things directly into existing models like Spark or Flink. You have all of the power of these operators, which can give you real-time analysis. By the way, all of this is without touching a hard disk, okay? It's all sitting in memory. And so it's proceeding at flat CPU memory speed. Great. So just a quick example of learning and prediction. Effectively, what's happening is we're going at the extreme left-hand of this diagram from raw data to state. And state is what we need for all these algorithms, really. And so the state of all the sensors at an intersection plus all of its neighbors effectively forms an input vector into my DNN. When we create this thing, we're going to create a new DNN, which is just got randomized lengths. And so it's untrained, and then start throwing vectors of state changes at it and get predictions up. And of course, the first time it's just a guess. But we have this opportunity to watch the real world evolve and backpropagate the difference. And if we do this a lot, then we get better. But more than that, we have the ability within each one of these things to track the error rate. And if the error converges, we're doing well. If it diverges, we're in bad shape. Okay? But we'll know about it. We'll know about it. All right. So what does an application look like? An application is a graph which is built by data, potentially of massive scale, hundreds of millions of these web agents, okay, which lives on this mesh of instances. And each one of these web agents is performing its own analysis and streaming its own predictions, analysis, whatever, responses back up through the broker or to a UI. Okay, so an application is a graph. Data flows over the graph and triggers the computation of insights continuously as data flows. Objects are stateful and concurrent, and we don't touch the disk. Okay, so we eliminate this huge big stack of horrible stuff, which otherwise we have to go and hang together, in adjacencies. Essentially, what SwimOS is a vertically integrated stack which runs everywhere, which takes a huge amount of the pain out of building these applications and the complexity of, I guess, the DevOps of deploying and managing the life cycle of these applications. It also saves us from having to push application layer abstractions back down into the infrastructure. Remember I said I don't like functions running inside the broker? Yeah, pretty obvious why. How many brokers do I need? And what if the broker suddenly gets busy doing something else? My application goes for a loop, okay? What I like is clear separation of concerns, and then, and then the processor can run at CPU memory speed independently. How do you use this thing? Well, from a developer perspective, this is just a bit of Java. Okay, Swim is effectively a set of Java extensions. You're defining and programming a little object-oriented model. And in the case of traffic, to go back to my example, you're defining what the relationship between a pedestrian crossing light, or an in-road loop and an intersection is, and you're describing what you want each intersection to do. But you're not describing what you want the whole of Palo Alto to do. So the whole program to consume huge amounts of raw data and predict from it is maybe 1,000 lines of code. Okay. So when data arrives, new actors, new concurrent objects get built by Swim, and each one deals with its own raw data and concurrently computes in a stateful way in memory. Okay. These web agents link and they collaborate to learn, predict, and respond. We haven't really talked much about response, but for us, for example, if you look at Palo Alto, our requirement there is that we're delivering a prediction which is within 100 milliseconds of real time. Okay, so these web agents then continuously stream real-time insights to UIs and to applications back into the broker. Okay, so my beginning slide, once again, Pulsar absolutely solves the problem of scalable infrastructure for delivering events from a bazillion sources, and that's a fundamental pattern. The business of computing over raw data is about building context and about building a graph of concurrent objects which can compute given dynamic relationships found in data. Okay, and SwimOS is an abstraction layer. It's Apache license. I'd love you to go and play with it, which allows you to do this. I'm going to stop there, and I'll be happy to take questions. Okay, so I see one question here, which is how to bootstrap agents with pre-trained states. Yeah, thank you. So you could load up a model using any technology you want. I mean, if you have pre-trained state, storing your states on disk or in some other form is very straightforward, and there's no problem at all getting a web agent or a set of web agents to load up anything from disk. You might do that when the application bootstraps, for example. Let me just read on the question here. Yeah, so reinforcement learning is the example here. By the way, it's entirely possible that you have powerful applications, investment in application analytical infrastructure, for example, in Spark. The key thing here is that you shouldn't have to throw it out. But if you said to me, cool, why don't I just use Spark streaming? I'll give you a counterexample in a heartbeat. This lack of clarity between data and state is key. If we're shifting all the data, say, to my Spark infrastructure, let me give you a really bad example. I could have one source, which is very influential in a prediction, but very terse, and another one, which is noisy and rather useless. And so at any point when I run my Spark streaming app or whatever it happens to be, the data is going to be flooded with mostly useless stuff. Okay, only rarely does my really important source say something and then I want to do something about it. So what matters most when we analyze things is state, okay, not raw data. What I want to know is the current state of the terse thing and the current state of the noisy thing. I don't care about the raw data. And so effectively, a good way to think about what SwimOS is doing here is that it's forming your state vectors for you, from which you can easily build tensors to put into other analytical algorithms or sketches or whatever you happen to be. I'll stop there. Are there any other questions?
I posted some in the chat.
Let me go there.
This is David.
Thank you, David. You saved me a bunch of effort.
No, great stuff. Great stuff. Love the presentation.
Can you read it to me, David?
Sure. So where in the infrastructure do the agents run?
Oh, so typically, so SwimOS is deployed in containers, typically on Kubernetes, close to a broker, right? And so now, in the example I gave you, where we're using SwimOS for a large mobile provider, we're running across availability zones, and even the cloud provider's Kubernetes infrastructure doesn't support cross-AZ use cases. But we're still linking these web agents at the application layer across availability zones because a web agent is a URI. Okay, its object ID is a URI. So typically we run, by the way, you mentioned a very interesting thing, David, about edge and cloud. Oh no, you use the term IoT. So IoT to me makes absolute sense when I know where the thing is. So for example, my traffic lights. But for a mobile use case, edge and IoT are meaningless, but I have lots and lots of edge devices. And the processing nonetheless has to happen in the cloud. So the whole idea here is that when we're not tying ourselves to a particular place, we could run in a hybrid configuration. And indeed, what Swim will do is move the web agents as close as possible to the raw data, so that we get this data to state conversion to happen early and minimize cost of transport and everything else. So in the case of traffic, for example, in Las Vegas, there are a couple of old Windows Server 2012 boxes in the Las Vegas city data center, which do the data to state conversion. And then the learning and prediction happens on a couple of Azure instances with GPUs attached. Okay.
A follow-up question on the, so everybody calculates state in these distributed functions. How do you account for time skew when you're comparing my state versus another state?
That's a great question. So Swim tries to solve this problem. Well, ultimately, we're going to get into acid in a second, which is horrible. What Swim does is the following. At any point in time, any web agent can compute using its own state and the state of anything it can see on its links. Now, that can be triggered by the arrival of data, by a moving window, by a trigger, or any other function of time. Okay. Let's just say I want to compute on the basis of time. And the real-time state of an adjacent intersection to my intersection happens to run on the instance on the other side of the country. Okay? So you see the separation between application layer and infrastructural concerns. It's possible that I'm half a round trip out of date. Okay? That is, an intersections model on some other instance in Seattle might have been updated, but it hasn't reached me yet. Okay. With Swim, data, well, at least the state of a web agent is at max half RTT out of date, and the model is eventual consistency. Okay.
Great. Thank you very much. Yeah, great presentation.
Thank you.
There was there's another question that came in through the Q&A. It says, how do you handle agent failures?
Great question. So agents are concurrent objects running in a VM, and we happen to run on the JVM or on Graal. But so agents don't fail independently of an entire instance failing. And when an instance fails, you could lose thousands or bazillions of agents. Okay. What happens in Swim is we're building this graph of concurrent web agents. That graph itself is continually persistent, but Swim recognizes that hard disks are probably 1 million times slower than computation. So that's an after the fact thing. So the model is continually being persisted, including the state of every web agent, as fast as we can on every single instance. And so if an instance fails, it can come back. It will come back with the state of the model just before it failed. Okay. The question then is this useful for transactions? And the answer is no, that's not the goal. The goal is eventual consistency and to ensure that over time, every instance learns the right state of the infrastructure.
Great, thank you. And one more, we're just a few minutes over time, but we'll ask this last question. It is, where can we learn more?
Oh, good, thank you. swimos.org is the Apache 2 codebase, and I'm Simon at swim.ai, happy to help.
Oh, do you have that on? Can we share that on the screen, or do you just want to repeat it?
Yeah, I'll bounce back. Give me 1 sec. Sorry.
Not a problem. I think it'll be great for people to just see the links and see your contact. Oh, perfect.
And Swim is swimos.org.
Okay, great.
Thank you. And
yeah,
thank you
you.
to the community. I mean, the Pulsar community is just fabulous. We love it.